Hey, my name is Tresden. I'm here today to explain something called resonance frequency. And I'm going to do a couple of demos today for doing resonance frequency. But one of the demos, real quick, is using my guitar. But first, let me explain what resonance frequency is. So resonance frequency is the frequency that a space, an object, or a volume likes to resonate at. You've probably experienced this maybe or seen it on an opera where the opera singer sings at a certain pitch and glass shatters around them. Well, that is because the resonance frequency of that specific object, in this case the glass, was reached to vibrate the glass back and forth and shatter it. To demonstrate this today, I have my guitar and I'm going to sing a pitch at this guitar, and this string is going to continue vibrating even after I am done singing. So my guitar tuning app happens to actually show the hertz at which each string vibrates at. So when I pluck my D string, this is a D string in the third octave. It's the very middle string on the guitar. It vibrates at 148 hertz on my guitar. So if I don't even touch the guitar, but I sing a D3 at the string, it'll start vibrating at that frequency and should resonate within the guitar. So the next part of the experiment is going to be finding the resonance frequency of my shower back there in the bathroom. To do this, we're going to need a couple numbers. First, we're going to need the width of the shower, which was measured with a measuring tape, and it was 41.5 inches. So that's our first measurement. Our second is going to be the speed of sound within the room. Speed of sound varies by temperature, so I measured the temperature in there using water and a thermometer. I left a cup of water in there for about an hour, and I got 68 degrees Fahrenheit. So it's 1 degree warmer in the bathroom than it is out here where it's 67 degrees. And then also, we plug those into our equation to find the frequency, the resonance frequency. In order to find the resonance frequency of the shower, what we need to do is take the speed of sound, which we know is 331 meters per second, and we take this times the square root of the temperature of the room over 273 degrees Kelvin. Now, plugging in our found value for our temperature of our room, we can determine what the speed of sound is in the room. So we take 68 degrees is what we measured, and we convert that to Kelvin, which is 293.15 degrees Kelvin, and we plug that in for T. So now we do the square root of 293.15 divided by 273, and that equals 1.0362, and we multiply this by the speed of sound in meters per second, equals 342.998 meters per second. So now, by taking our speed of sound that we measured in the bathroom in meters per second, we're going to convert that over here into feet per second, which turns out to be 1,125 feet per second. And then we plug that into our equation here, which is speed of sound times equals frequency times wavelength. Wavelength in this case is just wavelength equals 2 times the width of the room. So 2 times our width of the room, which was 41.5 inches. Now we're in inches here. We need to be in feet. So if we convert that and then plug this in for wavelength, we can find what we need. So let's do our equation here. So W, our speed of sound, feet per second, over 2 times our feet, which is going to be 3.45833 feet. I just took the 41 inches and turned it into feet here. So like a dummy, I said it equals the speed of sound. It's not. We already found the speed of sound. Speed of sound divided by lambda, which was the wavelength, equals our frequency. So that variable should be an f. There's our equation here, and we get what? 162.79 hertz. So somewhere around about 160 hertz should be the resonance frequency. Okay, for the sake of our experiment here today, what we're going to do is calculate next the uncertainty of our frequency here. So that's delta f of x. Now to do that, we're going to use this formula here. What we need to find first is this part, which is delta v, which is going to be the change in velocity. So to do that, what we took is our delta v here, and we took our known speed, or sorry, our calculated speed of sound within the room, which we found earlier in meters per second here, meters per second, and we also need to multiply that by the change in temperature. My thermometer was able to calculate within 1 degree Fahrenheit. So 1 degree Fahrenheit is converted to Kelvin here, and then that number is divided by 2 times our measured temperature in Kelvin, which was this is 68 degrees right here, 68 degrees, which is 293.15 degrees Kelvin. We calculate then that our delta V is 0.325 meters per second, but we need that in feet per second because feet per second is what we're using for the rest of our calculations. So we get 1.06 feet per second. Now that we know delta V, our other knowns up here is delta D here, which is just the difference between measurements in our ruler here, which was 0.1. And that converted to feet is 0.0083 feet. And then our D we know because we measured that, which is 41.5 inches, which is 3.4583 feet. All right. Now, if we take this and we plug those values in, and we take this and we plug those values in, we get 162.66 hertz, which we calculated earlier, times the square root of 0.00289 squared plus 0.00095 squared. And by completing this calculation, we should find delta f of x, which happens to equal 0.42 hertz. So that means our calculation could be plus or minus 0.42 hertz. So pretty accurate math on our part there. Our speed of sound, feet per second, over 2 times our feet, which is going to be 3.45833 feet. I just took the 41 inches and turned it into feet here. And then that will equal our speed of sound. So there's our equation here, and we get what? Let's see. Here we go. 162.79 hertz. So somewhere around about 160 hertz should be the resonance frequency. Okay, so first I'm going to play 160 hertz frequency through the speaker here in the shower, and we're going to see the resonance. I'll play one at 160, 200, 240, just so you can see the difference here. All right. So there's 160 hertz. Not nearly as loud at all. So if you couldn't hear it, I would suggest going back and watching this video with headphones. I would say that's a success. The resonance frequency was probably just around 160 hertz. It's probably closer to 162 hertz, but we couldn't necessarily get right at 162 because I don't have the means to play 162 hertz. But if I did, that's what I would do. There's a couple of errors here and there. That could be the humidity in the room. Since it is a shower, it could be more humid in there, affecting the speed of sound, objects in the way, etc. So also it's not an enclosed space, obviously the curtain's there, so a couple things play into that, but overall I'm happy with that experiment.